We're going to round out this unit by looking at something called quantitative analysis. And you can kind of see I've already, corrected a mistake on the notes. We're not looking at qualitative analysis. Qualitative deals with just looking at if something has happened. Quantitative analysis is about when we do a reaction, how much of a certain component of that reaction is present. So quantitative deals with numbers or how much of something is there. And you've already done something like this in lab quite a bit, actually. The first example we're going to look at are titrations. Just to kind of refresh, we used a burette to add a known concentration of what we call the titrant to an unknown concentration of what we call the analyte. And we know what the chemical reaction was. We'd have a balanced equation. We had a way to judge when the reaction was over. Remember the end point, we used an indicator to tell us when the reaction was done. And ultimately, all forms of qualitative analysis need to use stoichiometry. So everything we've talked about at the very beginning of this unit, we're going to be using tactics that you already know uh, to look at problems involving quantitative analysis. And so let's do a quick example. So here we have 25 milliliters of an unknown concentration of HCl is titrated to an endpoint with 17.24 milliliters of 0.150 molar NaOH. So what is the concentration of HCl? Well, the very first thing that we need in any stoichiometry problem is a balanced equation. So we're taking solutions of HCl and sodium hydroxide. This is just an acid-base neutralization reaction. So we're going to get a salt and water. And let's just kind of write down everything we know. We know everything about sodium hydroxide. We know how much volume we used to do this titration, and we know its molarity, its concentration. The only thing we know about the HCl is how much of that solution we used, or we started with. That was the analyte. And we're trying to figure out its concentration. So what's the first thing after you do the balanced equation? And let me make sure. Yep, this is balanced as written. What's the very first thing you do after that? Get to moles. And so we know everything about sodium hydroxide. So we're going to get to moles of NaOH to get us to moles of HCl. And once we know that, we can get to the molarity of HCl. All right, so how do we get to moles of sodium hydroxide? Well, we got concentration, so let's start there. That 0.150 molar means we have 0.150 moles of sodium hydroxide per liter of solution. That's the definition of molarity. And the first thing I'm going to do is get it in the milliliters because that's what I've been given. And the reaction says I used 17.24 milliliters of that solution. Now notice why I put it at the top of the fraction so that milliliters of solution can cancel out. And notice where I'm at. I got to moles of NaOH. So right now I'm here. How do I get to moles of HCl? Well, I'm going to use the balanced equation. The balanced equation says that 1 mole of NaOH is required to react with 1 mole of HCl. Those are the coefficients from the balanced equation. And so now if you look, I'm here at moles of HCl. All right. Well, how do I get to molarity? Well, I know that molarity is moles per liter. I already have moles on top, so I got to get to that liters on the bottom, but I'm given 25 milliliters of that HCl solution. I'll change that to solution here. And so I got to convert that to liters. 1,000 milliliters of solution is in 1 liter of solution. So milliliters cancel out. And look at the units I'm left with. I have moles of HCl over liters of solution. That's molarity. So I toss this, oops, what happened here? Sorry. I toss this into my calculator, and keeping track of sig figs, I get 0.103 molar HCl, or you could say moles per liter. But notice how I didn't do anything really new in terms of my approach to the problem. I used unit conversions, and I just used the basic concepts of stoichiometry of get a balanced equation and then get to moles. I can use the coefficients from the balanced equation to go in between the different parts of, or the different reactants or different products. All right, let's look at another type of quantitative analysis, and this is called gravimetric analysis. And this basically uses a phase change to find concentration. Now, that phase change is usually a precipitation reaction. So we're forming a precipitate. I say usually, that's not 100% of the time, but for this class, that's where we're going to be using gravimetric analysis. All right, so let's jump into the problem here. So there's a solid sample that contains an unknown amount of magnesium sulfate. We take 0.543 grams of the sample, dissolve it in water, and excess barium nitrate is added. All right, let's just kind of stop there and draw a chemical reaction for what's going on here. We're taking magnesium sulfate and dissolving it in water. And then we're taking barium nitrate, a solution of it, and it's telling you that you're adding a ton of barium nitrate, an excess, which means we don't have to worry about finding out which one's the limiting reactant. Magnesium sulfate is the limiting reactant. And then we got 0.734 grams of the precipitate. Well, what's the precipitate here? All right, let's think about what we're doing. We're going to do like a double replacement. The barium will go with the sulfate, and the magnesium will go with the nitrate. So go back to your table. I know it's kind of a few pages away or back from the previous unit. And look and see if one of those would form an insoluble precipitate in water. And that's going to be the barium sulfate. So sulfates are soluble, except barium is one of those exceptions. And then the question is, what is the mass percent of magnesium sulfate in the original solid? So let's refresh what mass percent is. It's grams of solute over grams of solution. Okay, well, the 0.543 here is our quote unquote solution. That's the sample. And this is essentially what we want to get to. So after the balanced equation, so we have a balanced equation here. What's our next step? Get to moles. Well, the only thing that we know about this chemical reaction is that we got 0.734 grams of barium sulfate as the precipitate. So what's kind of our flow chart here? All right, well, we're going to take grams of barium sulfate, get to moles of barium sulfate. I need to go back to the reactants to figure out moles of magnesium sulfate. Well, I can use the coefficients from the balanced equation to do that. And then I can get to grams of magnesium sulfate, which is what I'm going to plug in to right there. Okay, so let's set up a unit conversion to do that. So I start with what I'm given, 0.734 grams of barium sulfate. What do I use to get that to moles? The molar mass. Okay. Now, I probably would give you something like that because I know that you're masters of doing that, finding the individual atomic masses on the periodic table and adding them all up. So that's 233.38 grams of barium sulfate in 1 mole. So notice grams of barium sulfate cancel out, and I've gotten to moles. So there we go. Let's keep on going in our flow chart. How do I get to moles of magnesium sulfate? I'm going to use the coefficients from the balanced equation. That equation says 1 mole of barium sulfate is required to react with 1 mole of magnesium sulfate. So moles of barium sulfate cancel out. Notice I'm here now on my flow chart. And all I got to do is use the molar mass of magnesium sulfate to get to grams. So again, add up all the masses from the periodic table. And now I'm at the end of my flow chart. So let's do all this math. And that comes out to about 0.379 grams of magnesium sulfate. Now I'm not done because the question is asking about mass percent. I'm just going to take this number and plug it into my top term up here. So mass percent is the grams of solute, which I just found, divided by the whole solution or the whole sample, which the problem says it was 0.543. And then I'm going to multiply it by 100 to put it into a percent value. And that comes out to 69.7%. All right, let's take a look at one more type of quantitative analysis. And this is combustion analysis. As the name implies, we're going to burn something. We're going to combust it, usually in the presence of oxygen. So burn the reactants and weigh the products. Most commonly, this is used for compounds known as hydrocarbons. As the name implies, these are compounds that have carbon and hydrogen in them. So we're going to use this generic formula of X and Y for this formula. And the goal of a combustion analysis is to figure out what X and Y are. Now, the general reaction for a combustion, and this is something we've talked about, but I'll go through it again, is we take a hydrocarbon, and you can see in this diagram here, that's our sample there. Combine it with a lot of oxygen. So we put it in a furnace with a lot of oxygen. It burns and produces carbon dioxide and water. Now, in this diagram, we can see that the water is trapped by some absorber. They take the mass of that, they can figure out how much water was produced. And you do the same thing with carbon dioxide. Carbon dioxide goes through the first absorber. It doesn't get absorbed by water, but gets absorbed by something like sodium hydroxide, and they can calculate the change in mass of that. Okay, so the um, goal here is to find the masses or have those given to us of our products. We can go to moles and then figure out how many moles of carbon we have and how many moles of hydrogen we have. Because that's this carbon here in carbon dioxide is the same as this carbon here in the reactant. This hydrogen here is the same as this hydrogen in the reactant. So if we know moles of carbon and moles of hydrogen, we can find the empirical formula. So let's do a problem like this. So we're taking some sort of hydrocarbon and combusting it in oxygen to produce carbon dioxide and water. So this tells us that we produce 0.00788 grams of carbon dioxide and 0.00322 grams of water. Okay, so the first thing we're going to do is get to moles. All right, so let's get to moles for carbon dioxide. We're going to take what we're given, use the molar mass. And what we want to get to, though, ultimately, is moles of carbon and moles of hydrogen. So if this conversion here has got me so far to moles of carbon dioxide, how do I get to moles of carbon? Well, I know that 1 mole of carbon dioxide contains 1 mole of carbon atoms. That's what the formula tells me. One molecule of CO2 has 1 carbon. So 1 mole of CO2 has 1 mole of carbons. So notice everything is canceled out, and I've gotten to moles of carbon. I'm going to do the same thing now for hydrogen. So the thing that contains hydrogen is water, and the problem tells me I got this many grams of water from the reaction. So I'm going to get to moles of water by using the molar mass. So grams of water cancels out. How do I get to moles of hydrogen? So I know that 1 mole of water, according to the formula, molecular formula, each mole of water has 2 moles of hydrogen. Okay. Now, these are not my subscripts here in the original hydrocarbon. What do I do with these to find the empirical formula? I'm going to compare their ratios. Remember, I take each number. This one's a little bit easy because there's only 2 elements. I take each element and put it over the smaller number of moles. So for hydrogen, that looks like this. And that gives me a ratio of about 1.99. That's really super close to 2, so I'm just going to call it 2. And I'm going to do the same thing for carbon. In this case, it's the same thing over each other. So that comes to 1. And that basically tells us the subscripts in our empirical formula. 1 carbon, 2 hydrogens. And that's our empirical formula. We don't have enough information to figure out the molecular formula, but this is kind of where we will will take it with these kinds of problems. We won't worry about going to the molecular formula. So that will conclude this chapter. Again, this whole chapter was virtually all math. So I highly encourage you to go through the practice problems, go through the assessment practice, go through problems in your textbook, and you'll to get practice for this because this is something that you're going to be doing over and over again, even in subsequent chapters. You cannot get away from stoichiometry.